Here, use the derivative to find the critical points and the inflection points. The first function is x cubed minus 9 squared plus 24x plus 5. So first, we need to find a critical point, and then second, we need to find the inflection point or points. So for first, we will find the critical point. So remember, a critical point is where the first derivative of our function is 0, or it is where it's undefined. So let's take the derivative. Derivative is going to be 3x squared minus 9 multiplied by 2x plus 24. Now, notice here we can also factor 3. So that's what I'm going to do in the next step. Going to be 3 multiplied by x squared minus 6x and then plus 8. Now, notice this function is defined for all values of x. So, what we have to care about now is where the first derivative is equal to 0. That will result in x squared minus 6x plus 8 equal to 0. Now we need to factor this formula. So what I want to find two numbers. If I multiply these two numbers, that will result in the number 8. Then I have added these two numbers, it will result in minus 6, which is in the middle term. So these two numbers are going to be minus 2 and minus 4. Multiply both of them, going to be 8, and then if I subtract them, going to be minus 6. So the factor of this equation going to be x minus 2 and x minus 4 equal to 0. In case of x minus 2, x going to be 2. And in case of x minus 4 is 0, it's going to be x equal to the 4. Now, these 2 points are our critical points. So this is the first part of the question. Now what we need to find is our inflection points. So remember again, this is the first derivative, and then the inflection point is where the second derivative is 0 or where it is undefined. And also we need to do a test to confirm it's an inflection point. So second derivative, notice the first derivative, the second is just the derivative of the first, so it's going to be 3 multiplied by 2x minus 6. This is just using the power rule. Now notice this function is defined for all values of x, so the only thing now we have to care about is where the second derivative is equal to 0. That's gonna be 2x minus 6 equal to 0, and then 2x equal to 6, and divided by 2, x gonna be equal to 3. Now x equal to 3, it's a possible inflection point. To confirm it's actually an inflection point, we need to do a test. In this test, what I'm gonna do, I'm gonna take values that is larger than x equal to 3 and lower than that, and I want to know the signs of the second derivative. If the sign changes, then it's inflection point. If not, then it's not inflection points. So this is the x-axis. I mark our possible inflection point, and then I want to take values that is larger than our possible inflection point and lower. So here in this case, I took 4 and I took 0. This is just randomly selected. Just has to be a value that is larger than our possible inflection point and less than our possible inflection points. So I'm gonna evaluate 0 and 4 in our second derivative. So in case of 0, this term gonna be negative and this term is positive, so negative multiplied by positive is negative. And then in case of 4, gonna be 8 minus 6, which gonna be a positive number, and positive gonna be a positive number, and positive multiplied by positive is positive. So now I'm gonna mark our number line x-axis, so I mark negative and positive. So what we can see here, the second derivative signs changes when we go values that's higher than x equal to 3 or lower. Therefore, this is an inflection point. Now for the part number 2, we have f of x equal to x to the 5 minus 10 x to the 3 and then minus 8. So again, what we want to find is 1, where's the critical point, and 2, where is our inflection points. So first, our critical point again gonna be where's the first derivative is 0 or where it is undefined. So what I'm gonna do here, I'm gonna take the derivative of the given function. It's gonna be 5x to the 4 minus 10 multiplied by 3x squared. Now, what I'm gonna do, I wanna factor a smaller term, so it's gonna be x squared, and then we're left with 5x squared minus 30. Now this is the first derivative. So now we have to think where the first derivative is undefined. This function is actually defined for all values of x. So the only part we have to care about is where the first derivative is equal to 0. So our first gonna be x when it's 0, and then 5x squared minus 30 is 0, and we're gonna solve this equation. So I'm gonna move 30 to the other side, and then I'm gonna divide on 5 both sides, and then gonna be, when we take the square root, it's gonna be positive or negative square root of 6. So now we have 3 critical points: x equal to 0, and x equal to square root of 6, and x equal to the negative square root of 6. These are our critical points. So now, again, this is our first derivative, and we need inflection points. Remember, inflection point is where the second derivative is 0 or it's undefined, and also we need to do a test. So let's take the second derivative. Remember, the second derivative is the derivative of the first. This is just using the power rule. It's gonna be 20x to the 3 and then minus 60x. Here I can factor the term 20x, and we're gonna be left with x squared minus 3. This is again our second derivative. So we notice here this function is defined for all values of x. So what I want to care about now is only where is the second derivative is 0. It's gonna be 20x multiplied by x squared minus 3 equal to 0. First, we'll take the first term, 20x, gonna be it's equal to 0, and then we take x squared minus 3 equal to 0, and then I'm gonna move 3 to the other side. I'm gonna take the square root, it's gonna be x plus and minus square root of 3. So now we have 3 possible inflection points: x equal to 0, and x equal to plus and minus square root of 3. So now, to confirm they are an inflection point, what we want to do is to do the test. So what I'm gonna do, I'm gonna take the second derivative, and then our possible inflection points are again, they're gonna be 0 and plus and minus square root of 3. Here, square root of 3 is approximated to be 1.7. So when we have the x-axis here, I want to mark our possible inflection points. Again, gonna be x equal to 0, x equals square root of 3, and x equal to the minus square root of 3. Now I'm gonna take values that is larger and lower, and between these values to check the signs of the second derivative. If the signs of the second derivative changes around a point, then it's an inflection point. So in the middle between square root 3 and 0, I'm gonna take 1, then I'm gonna take minus 1, and then minus 2, and then to the right I'm gonna take 2. Again, these values are between and larger and lower than our possible inflection points. I'm gonna take these values and evaluate them in our second derivative, and I want to see the signs. So first I'm gonna take x equal to minus 2 and plug that in the second derivative. Notice this term in here gonna be 4 minus 3, which gonna be a positive, and the first term gonna be a negative. So negative multiplied by positive is negative. Then I'm gonna take second derivative evaluated at x equal to minus 2. The second term gonna be positive 1 minus 3, which gonna be negative. And then the first term gonna be negative. So negative multiplied by negative is positive. Then I'm gonna evaluate the second derivative when x equal to 1. So the second term gonna be 1 minus 3, which is negative number, and then we multiply it by the first sign, which is positive, and that gonna be a negative sign. Now we evaluate the second derivative at x equal to 2. So second term gonna be 4 minus 3, which is gonna be a positive number, and the first term gonna be a positive. So positive multiplied by positive is positive. Now I'm gonna mark these signs in our number line or x-axis. So now what we notice that at each of these points, square root of 3 and negative square root of 3 and 0, there is changes of the sign in the second derivative. Therefore, all of these 3 points are actually our inflection points for the given function. For 3, we have f of x equal to 5x minus 3 natural log of x. Again, we want to find critical points, and then second, we want to find the inflection points or points. So first, critical points. Critical point gonna be where the first derivative is 0 or where the first derivative is undefined. So let's take the derivative of the function. It's gonna be 5 and then minus 3, and then the derivative of natural log of x is just 1 over x. That's the first derivative. Now, where the first derivative is undefined, it's gonna be when we have a fraction, it's gonna be when we have a number over 0. So when x is equal to 0, However, here what we notice, x equal to 0, it's actually not in the domain of the given function of x, because we cannot take the natural log of 0. It is undefined. Therefore, this point x equal to 0, it's not a critical point. Again, because it's not in the domain of our function. So now what we left off with is where the first derivative is equal to 0. That will result in x equal to 3 over 5. And that's our critical point. Now for our inflection point. Again, inflection point is where the second derivative is 0 or where it is undefined. So let's take the second derivative. Here we are giving the first derivative on the top. And remember, inflection point is also, we need to do a test to determine if it's actually an inflection point. So let's take the derivative here. I wrote 3 over x as 3 multiplied by x to the negative 1, so it is easier to take the derivative. And the second derivative gonna be 3 over x squared. Now note this function is not defined when x is equal to 0, since the result in 3 over 0, which is not defined. But remember again, x equals 0, it's not in the domain of our function of x. Therefore, it's not an inflection point. So we just have to find where is the second derivative is equal to 0. And noting here that x squared is not gonna be equal to 0. It's never. This number here can, if you like positive values or negative values, it's gonna be always positive since it's squared. Therefore, this term is never 0. This means that we don't have an inflection point for this function of x. And 4, we have f of x equal to 4x multiplied by e to the 3x. So remember, we need to find a critical point, and then we need to find the inflection point or points. So again, a critical point is where the first derivative is 0 or where the first derivative is undefined. So the first step to find the critical point is to find the first derivative. So to take the derivative of x, notice these are two multiply functions, so we're gonna use the product rule to differentiate the function. So I'm gonna set u to be x and v to be e to the 3x. I'm gonna take the derivative of each. Now, since I already found all the functions, I'm ready to apply the product rule. It's gonna be 4 multiplied by the product rule, which is u prime by v plus u multiplied by v prime. gonna be 4, and then multiply 1 by e to the 3x, which is just e to the 3x, and then plus x multiplied by 3 e to the 3x, which is 3x e to 3x if I arrange the terms. And then I'm gonna factor e to the 3x. Now this is the first derivative. So notice here, the first derivative, it's defined for all values of x. So the only thing we have to take care about here and the critical point is where the first derivative is equal to 0. So we'll set the term 4e to the 3x multiplied by 1 plus the 3x equal to 0. Notice this first term, 4e to the 3x, it's never 0. If you like x to be 0 or a positive values or a negative value, e to the 3x gonna be always positive and never 0. So we just have to equal 1 plus 3x to the 0 and solve that equation. X gonna be minus 1 over 3, and that's our critical point. Now we need to find the inflection point. So remember, this is the f prime of x. So again, inflection point is where the second derivative is 0 or where it is undefined. Plus we need to do a test to make sure that the signs of the second derivative changes around our inflection points. So first we need to take the derivative of the first derivative, which is the second derivative. To do that, we're gonna use the product rule. So remember, f prime of x is gonna be 4e to 3x and then multiply by 1 plus 3x. So I'm gonna take the first term and assign it to k, and the second term I'm gonna assign it to h. Now what I'm gonna do, I'm gonna take the derivative of each. So I'm gonna use the chain rule here. And then for h, I'm gonna use the power rule for 3x. Now I'm ready to apply the product rule. So I'm gonna take k prime, multiply it by h, and add it to k multiplied by h prime. So that's gonna be 12e to the 3x multiplied by h, which is 1 plus 3x, then plus k, which is 4e to the 3x multiplied by h prime, which is just 3. And then gonna be 12 plus 12e to the 3x, and multiply 3 by 4. Now what we notice, we have similar term, so we'll factor 12e to the 3x, and we'll left off with 1 plus 3x and then plus 1. Now we have 1 plus 1, which results in 2 plus 3x in the parentheses. Now, what we just found is the second derivative function. So notice, this function is defined for all values of x. So what we care about now is where the second derivative is 0. So we'll set the second derivative to 0 and solve that equation. So again, the term here, the first term, 12e to 3x, especially e to the 3x, it's never 0. We can try 0 for x and can positive value or negative value, it's gonna be always positive. So I'm gonna just set the second term to 0, and then x is gonna be equal to minus 3 minus 2 over 3. And this is a possible inflection point. So how to confirm? We need to do the test. So again, x is our possible inflection point. We're gonna be minus 2 over 3. Then I'm gonna draw the x-axis. I'm gonna mark our possible inflection point, and note here, negative 2 over 3, it's approximate to be negative 0.667. So now what I'm gonna do, I wanna see what are the signs of the second derivative around this possible inflection points. So I'm gonna pick a value that is larger than x and then a value that is lower than x, and I want to see the signs in there. So here I picked positive 1 and negative 1. Now I'm going to evaluate negative 1 and positive 1 into the second derivative. Remember the second derivative function, which is this one in here. Now for x equal to negative 1, remember the first term is always positive. So only care about the second term. Here, gonna be 2 minus 3, which is gonna be negative number. And then positive multiplied by negative number is negative. Now I will do x equal to 1. And the second term gonna be a positive number. And again, the first term is positive. Positive multiplied by a positive, it's a positive. Now I'm going to take these signs and put it in the x-axis, and we can see the signs of the second derivative changes around x equal to negative 2 over 3. Therefore, this is actually an inflection point.